Okay, folks, in this video we're going to go over exponential functions. Alright, exponential functions, what do they look like? Exponential functions have the following format. So an exponential function is where we have f of x is equal to b raised to the x power. So basically an exponential function is a function where the power, the exponent, has to change over time. It's variable. Okay, so this b in this formula is called the base. So the base has to be greater than 0. So our base has to be positive, and our base cannot equal 1. So those are the rules for an exponential function. Your base has to be positive, and your base cannot equal 1. Let's look at this. Let's look at just kind of a basic graph of just a general exponential function. Okay, so this is going to be a graph of f of x equals b raised to the x power. And it turns out this is what the graph looks like. We have a horizontal asymptote at y equals 0. So that means that an exponential, at least in this form, never touches the x-axis. And it turns out that we have a y-intercept at y equals 1. Okay. So an exponential graph looks like this. All right. So there you go. So that is your basic exponential graph. What are some quick facts that we can gather from that graph there? Okay. Well, we already said that the horizontal asymptote is the equation y equals 0. We approach the x-axis, but we never cross it. The domain of an exponential function. Well, the domain here will be, remember, domain is your set of your x values, set of your independent values. Well, this goes infinitely to the left and infinitely to the right in terms of x values, so our domain is all real numbers. Negative infinity to positive infinity. The range of an exponential graph will be, or of this basic exponential graph, will be, let's see here, so we get close to a y value of 0, but we never quite get there, so it's going to be parentheses 0, and we go up infinitely, so that's why our range is from 0 to infinity. All right, so that is kind of your basic information about an exponential graph. And later on, we're going to talk about what transformations do to this graph. But what I'm really interested in, especially in the homework, is that there is a special base that has a lot of applications in math. And that base is called E. So let's talk about that really quickly. There's something called a natural base E. Okay? And it turns out that E, it's not a variable, it's not like an x, but E is an actual number. E is kind of like pi. It's one of those numbers that just goes on forever and ever and ever. So it turns out, in fact, let me show you how to calculate E. Let me open up my calculator here. All right. So if you have a TI 84, 83, your E, if you notice on the left side of your calculator, kind of towards the bottom, you see log and ln. We'll specifically look at that ln. We'll talk about that in the next lecture. But ln stands for natural log. And above the natural log in a different color is e to the x. So I'm going to hit second ln, and that's going to bring up my e. I'm going to raise it to the first power so we can get an idea of what e equals. And this is an approximation. Like I said, that decimal goes on forever and ever. Our calculator just doesn't have enough room to put all the decimal places because it never stops. All right, so e, let's go back to our notes here. So e is approximately, that's what those curvy lines mean there. E is approximately 2.718 and some change, right? It goes on forever. All right. So like I said, a lot of the lectures after this will be based off this natural base e, so I wanted to introduce it now. For example, suppose we're asked to calculate e to the negative 3.2 power, round our answer to 3 decimal places. Okay, e to the negative 3.2 power. So we're just going to repeat what we did before. Second ln, I want to raise it to the negative, remember your negative's at the bottom, 3.2. All right. Into 3 decimal places, this is a 0.041. 0.041. All right. So that's how you calculate e to that power. All right. Let's keep it moving. Here we go. Sketch the graph of f of x equals 2 minus e to the negative x. All right. So this will be a nice little refresher on how we perform transformations. So the first thing I'm going to do here is actually I want to start off with a graph of just the regular e to the x function. Okay. So my green graph here is a graph of e to the x. Okay, so remember b to the x, it has the same shape. Okay. So now let's identify the transformations that we need to do to this e to the x graph. So I'm going to come back up here to the original function. I'm going to rewrite it like this. It might be a little easier for you to see the transformations if I rewrite this as a negative e to the negative x plus 2. All right. Okay, so what are the transformations? Okay, so the negative on the outside of our function, if you recall, means that we need to reflect the x-axis. Okay, that comes from the negative. Okay, let me see if I can do different colors here. The negative that's on the inside, as I call it, but the negative that's attached to that power there, that's also reflection, but that means we need to reflect the y-axis. Okay. And then lastly, the plus 2 means that we need to then move our graph up 2. All right? Okay. So I'm going to try to put all of these transformations onto the same graph here. Okay, so red, we're going to reflect the x-axis. So what that means is that as I reflect this over the x-axis, just imagine taking that graph and just flipping it over the x-axis. The new graph becomes something like that. Actually, let's make that a little better. We're still going to approach that horizontal asymptote, and we're just going to come down. So that is our x-axis reflection, where right here is a y value of -1. Okay? Now let's reflect the y-axis. I'm going to do that in blue. Okay, so I'm going to reflect the red graph now over the y-axis. So now what that means is take that red graph and just flip it over the y-axis. Flip it over the y-axis. So now that should look something like this. We're still going to go through that -1, but now we're going to approach the horizontal asymptote on that side. Okay? And then now, lastly, we have to take that blue graph and we have to shift it up 2. And I'm going to do that in a different color. I'm going to do that in this weird pen-looking thing. Okay. So now we're going to move the blue graph up 2. And that means that -1, that y-intercept of -1, now becomes at a positive 1 now. So I'm going to take, so what I did was in the purple there, I took that y-intercept of -1, I moved it up there. And also notice our horizontal asymptote is going to change. Because as we move this thing up and down, the horizontal asymptote changes. So as I bump this up 2, my new horizontal asymptote is going to be at y equals 2. You see that? That comes from me moving my initial horizontal asymptote of y equals 0 up 2 units to y equals 2. All right. So then now putting all that information together, just take that blue graph, bump it up 2 units, and we should get the following graph. Something that does, let's see here. And there we go. That multicolored graph is our final answer there. Okay. All right, so on the homework, you're going to be asked to select the correct graph, and hopefully that clears up how you perform the transformations. All right. Here we go. Okay, so last little example here is we can use exponential functions to figure out how much money we're going to have in our account if we do an investment. Okay, so consider this. For example, suppose $10,000 is invested at an interest rate of 3.5%. It's compounded semi-annually. What is the value of the investment after 5 years? Well, to calculate the value of this investment after 5 years, we have to do something that's called discrete compound. Discrete compound interest. And this tells you how much you're going to have in your account after a certain amount of time. And here is the formula. It's A of t, the amount of money in our bank account after t years, we'll write out all the variables in a second, is, it's our principal, times 1 plus r over n raised to the nt power. Okay? All right, so a whole lot of variables going on here. So what is P? P stands for your principal. In our example here, it's going to represent the initial amount, the initial deposit. Uh-oh. It's going to represent the initial deposit. All right, that's what P represents. R represents your interest rate. And please keep in mind, always write your interest rate. It's given to you as a percent. Always write it as a decimal. Okay. N is the number of compounds in a single year. So what is a compound? A compound is just how many times do they calculate the interest on your investment, okay, within a year. So semi-annually means we're going to calculate interest twice a year, right? Semi-annually means twice a year. Quarterly means 4 times a year. Annually means 1 time a year. And daily means 365 days a year, not including a leap year. Okay, so N comes from how many times you want to compound in a year. And then T, as you probably guessed it, represents time. And for us, it's often going to be in the time scale of years. Okay? All right, so putting all that information together, we know that we are trying to calculate the amount in our bank account after 5 years. So they want us to calculate A of 5, which equals our P, our initial deposit. We put in $10,000 times 1 plus R, our interest rate. So 3.5% is 3.5%, which I have to write as a decimal. And if you recall, with percents, you just take your decimal place, move it 2 spots to the left, or divide it by 100 in your calculator if you don't want to do it that way. But you should get a 0.035. That's 3.5%. So once again, take the percent, divide it by 100. That's how you get your percent as a decimal. So 3.5% divided by 100. That's what I told you, 0.035. All right, so we're going to take 0.035, and we have to divide it by N, the number of compoundings in a year. Since we're doing it semi-annually, this is why it's 2. And it's raised to the N times T power. So 2 times, actually what I'm going to do right now is I'm just going to put a T for right now. I'll explain why in a second. Okay, so in your homework, they're going to ask you to come up with the equation for A of T. So let's do it like this. Let me just change that 5 to a T right now. Let's do it this way. Okay, so in your homework, what you're going to have to do is go ahead and figure out the parentheses. So this will be 10,000 times, let's go to our calculator. If I take 1 plus the 0.035, divide that by 2, and enter, we get 1.0175. And we're going to raise it to the 2 times t power, because the power is n times t. Okay, so that is our equation. So on the homework, if they ask you for what's the equation, this is what you would type in. But now let's answer the question, what's our amount after 5 years? All we have to do now is plug in 5 for t. 175 times 2 times the 10th power. Okay, we're going to round our answer to 2 decimal places. So it's going to be 10,000 times a 1.0175, and this is raised to the 2 times 10 power. Now I will say this, if you have a calculator where it doesn't bump you up as a superscript when you do your power notation, make sure you put the 2 times 10 in parentheses. Okay, when you hit your power button, make sure, matter of fact, let's do that. What I want you to do is 10,000 times 1.0175, and we're going to raise it to the 2 times 10 power. We put that in parentheses. For folks that have a calculator that looks like mine, you don't have to do the parentheses, but folks where you don't have that, the parentheses is absolutely necessary. All right, there we go. We get 14,147 and 0.78, 78 cents. So 14,147. And 78 cents. There we go. So that's how we use exponential functions to calculate values of investments after a certain amount of years. All right, folks. See you guys in the next video.